Just as Jocelyn said, I am currently working as a postdoc with Kevin King with USDA ARS in Columbus. Yes, today's talk is going to cover really some of the more in-depth analysis that we're doing on our edge of field research sites. So what we're going to talk about today is the effect of rainfall and ground cover, looking at the magnitude of different surface runoff and tile runoff events. How do these two factors kind of each individually affect the size of events that you would see coming off of a farm field? So the first kind of thing we're going to talk about really are surface runoff events, and then we're going to talk about how they're tied to the size of the rainfall event. Our ground cover actually was not statistically significant, which we'll talk about that a little bit more. Magnitude of tile discharge events were tied primarily to antecedent rainfall conditions. And finally, we saw grass-type cover crops associated with lower tile discharge. So we're going to talk about each of those points more in detail, but this is kind of the big picture look at what I'm going to talk about today. So as you know, in Northwest Ohio, we have a lot of times of the year when we've got excess water in the soil profile. So this photo really just shows in one image a field in March with extra surface water ponding on the surface. There's definitely tile drainage happening, and there probably was some surface runoff happening before this photo was taken during the rainfall event. Our edge of field research sites, we've got all of them outfitted with monitors at both the tile outlet and flumes to collect surface water as it collects off the field, and it's directed into a flume so that we can catch and measure all of the quantity of water that's coming off of the field. So once this water leaves the field, this is kind of the broad importance of why we're looking at this. Once the water leaves the field, it enters surface ditches like the one you would see, and once you get past the field level, we don't really have a lot of opportunity to intercept that water. It goes straight down rivers like the one you see in the top corner, and eventually ends up in Lake Erie, and that concrete structure that's a little bit difficult to see in the bottom right-hand picture is the water intake for the city of Toledo. So that's what had to get shut down in 2014 for 3 days because algal toxins ended up in the lake. So the water that comes off of the fields in the western Lake Erie Basin ends up directly in line in the pathway of this water intake. So this is kind of why we care about what's coming off of our fields. And again, this is just another picture to show Lake Erie. And this photo, it's not, the color is real. That is green lake water that you see in the image. This was taken this past summer. We got an opportunity to go out on some charter boats and talk with some charter boat captains about what they're seeing out on Lake Erie. So I just wanted to also share that photo with you guys who can't go out on the boat. And yes, the water really is that green. I think that's something that's really important to think about. Everything is all connected with one another. And even though we're in the headwaters of the watershed here, eventually everything goes to one place. Okay, so kind of back to more of the topic that we're going to talk about today. Our Edge of Field Research Network has 20 paired field sites. That means we have 40 individual fields that are monitored to be monitoring all the surface water runoff, volume, and nutrient concentrations all the time, and we're monitoring every 10 minutes. We take a sample of the discharge and the phosphorus and nitrogen quality of the water, and again we have at each of those fields we have a surface flume and tile discharge monitoring. These edge of field locations are spread all around Ohio. Most of them are within the western Lake Erie Basin boundaries, but some of them are also outside. Some of them out in London, Ohio to the south, and some of them kind of more in the Delaware County, Morrow County area in central Ohio. So we really span all of that corner of northwest Ohio that's intensely tile drained. These are just some of the results that we've seen off of these sites to characterize the total volume that we're seeing over an annual, monthly to seasonal basis. it might be a little bit hard to see. I know this is kind of a small screen for all those of you who are all the way in the back. But the important thing to kind of take away from this message is most of our water is coming through the tile drainage system when you're looking on both a seasonal and an annual basis. So the tile discharge really becomes our primary water loss pathway. But we can't forget about surface runoff either. About 8% of our annual precipitation does leave the field as surface runoff. So we can't forget about that part. It's not negligible. So we have to be thinking about that as well. So the statistical analysis that I did, it goes without saying that there's a lot of factors that are going to influence the size of a discharge event, whether it's from the surface or the tile. So the approach that we took was a multilinear regression analysis. That's a big fancy name for saying that we, instead of fitting one x to one y and drawing one straight line through it, we fit one y with many x's, and you kind of stack all those lines on top of one another, and you can relate how well each of them impacts the individual y as you are going through that statistical analysis. So it's a very commonly used statistical format. It might be a little bit different than what you guys see other presenters talk about, but it's one of the best ways we have to be able to control for the different factors that we're seeing. Because if we have a sandy clay soil versus a heavy clay soil, you can actually factor that into the analysis before you carry it out, so you don't have all these confounding factors of tillage and season in your analysis. And then the final result that comes out is really a relative influence of different characteristics, so you can directly compare the effect of rainfall versus the effect of ground cover. So our preliminary results for this analysis, the effect of rainfall that is happening on the size of discharge events. This graph is a little bit busy again, but I'm going to walk you through it. This graph is showing us the black line that goes from the left to the right. Here you can see this black line here. It is telling us the size of rainfall events, and they're all ranked as an exceedance percentage. So 100% of the events are exceeding about 10 millimeters is how you would read that on the far right-hand side. And then when you kind of look at those colored lines, the blue line and the green lines, those tell how much surface discharge, what percentage of the total surface discharge we're seeing during rainfall events. The big take-home from this graph is that the majority of our discharge is happening during a minority of rainfall events. So the 20% of the events exceed 30 millimeters, and then but we have most of our discharge happening during those events. So just how you would read that is that surface discharge line. If you pull it over to the other side, 65% of our surface discharge is happening in 20% of rainfall events. And our subsurface discharge, about 40%. And that translates to DRP load, with surface DRP load having just under 60%, and our subsurface DRP load coming in about the same as their surface discharge. So that's just kind of talking about rainfall playing a major role in our phosphorus losses and our discharge. Okay, so we throw that into our statistical model. This shows us one of the things that's maybe not very surprising, but we are able to see this with the statistical analysis, is that the size of the rainfall event is directly related to the size of the discharge event. So if you have a higher rainfall, you're going to have a higher surface discharge. And I think that logically makes a lot of sense. One thing that you didn't see is we actually didn't see the impact of maximum rainfall intensity on the size of the rainfall event. It really was more tied to how much volume was landing on the field, as opposed to how fast it was landing there. For tile discharge, we actually saw a little bit of a different effect. It was less tied to the size of one rainfall event and more tied to a series of events happening in short succession. Really a 48-hour period, so 2 days a 2-day period, if you have a lot of events, that's when we started to see more tile discharge happening. Again, might not be very surprising, but these are things that we don't always think about. If you have a high rainfall event, you might think automatically that's going to lead to a high tile flow, but that's not really what we see. We actually see that if you have high rainfall events happening in short succession, then those lead to greater tile flow discharges. And our single events, one rainfall event that's isolated from other events, and short duration events, events that might have a lot of volume but don't happen over a long period of time, they really don't influence a lot of tile discharge. So to kind of change gears a little bit and talk about ground cover, our ground cover results that we saw were that they actually didn't have a statistically significant effect on how big a rainfall event, or on how big the discharge event was. So it doesn't really matter. Once you have a rainfall event happening, it doesn't matter what ground cover you have out there. The discharge volume is going to be related more towards the size of the rainfall. And that is kind of to say, kind of that asterisk down there, it doesn't tell us about event frequency. So I'm not saying if you have a cover crop that you're going to see the same number of events. We don't actually know that from this statistical analysis, but what we do know is that once surface runoff is happening, the size of the event doesn't depend on if you have a cover crop out there or not. But for tile discharge, again, we saw a little bit different story. All of our grass type crops, that included our corn, wheat, annual ryegrass, cereal rye, all of those crops were associated with lower tile discharge. So everything that kind of fell into that grass type category, and again, didn't really depend on what season it was, we saw lower tile discharge when you had a grass type crop growing. And that effect was stronger than for our legume-based crops. We also looked at kind of soybeans and clover. Those, while they also reduced tile discharge, it wasn't as strong of an effect, and that's where we talk about this relative statistical amount. Our grass-type crops really were associated with lower tile discharge. So what this tells us is that, if you want to reduce your tile flow, something like a grass cover crop might be your best bet. And we also kind of could see, because we're ranking all of these effects, the ground cover has less of an effect on the size of discharge events compared to rainfall characteristics. Okay, so this is again just kind of that summary I went through at the beginning. I'm going to tie this back in a little bit to some of kind of our bigger picture edge of field research data. This is kind of our really in the weeds level data analysis here. But the big take homes, if you have a surface runoff event, it's going to be primarily determined by a single rainfall event. And your tile discharge is really going to be determined more by short events in succession. And if you have crop type cover crops or grass, corn, anything growing out in the field is going to eventually lead to lower tile discharge. Okay, so then how does this all relate back to, again, this is another photo of Lake Erie. So out of our edge of field sites, this is the results of 142 site years of data. Our total phosphorus load that we saw off of the sites. When you look over the entire year, tile discharge contributes more of a total phosphorus load than surface runoff does. But we also can't really forget about, again, like I mentioned at the beginning, those surface runoff events. If you start thinking about the fact that high rainfall events are going to cause high surface flow events, that's really what's going to cause these outlier points that are happening at the top of the graph. These events do have a big impact on water quality, so we have to be aware that the high rainfall events are going to cause these high runoff events. Whereas, if we want to kind of reduce our total phosphorus loads all throughout the year, then you want to maybe be more focused on the tile discharge and reducing that overall volume of water that's going through the tile drains. And we see the same type of story for our dissolved reactive phosphorus load. Overall, if you take the year, looking at a whole over the year, our tile drains are flowing all the time in Ohio. So when you start to say each time the tile is flowing and it's a low concentration, you're losing a little bit of phosphorus, and that adds up when you start accumulating that over a 6-month period and over the year. So when you're really trying to reduce those dissolved reactive phosphorus loads, reducing your tile discharge is going to give you results. But for surface runoff, you also, again, can't forget about those. Just to kind of reiterate, those single surface runoff events can contribute to a lot of dissolved reactive phosphorus load and total phosphorus load. So you kind of need to be, when you're thinking about water quality, it's a system. So you can't really just focus on one thing. And this is again why you might hear some of the speakers also echoing this, there's no silver bullet. Because there's no silver bullet that's going to be able to reduce your daily tile discharge loads of phosphorus and your heavy surface rainfall events. So with that, I just want to credit, all of our partners. There's a great team that goes into making this edge of field research happen every day, and a lot of research partners that we have, and we really couldn't do this without the support of the greater community. So, and thank you all in the audience too for being here, listening, and contributing to our research. Thank you.